Hello everyone, continuing our integration by parts discussion. In this video, I will discuss a shortcut method, also known as table method or DI method, uh, that we use to find the integration by parts. So this method is really helpful and really quick if you have to do repeated integration by parts in any question. But obviously, it will work for even the cases when you only need integration by parts only once. So previously we learned that if you only do it once, so integration by parts, so if you have integral of u dv, that is equal to u times v minus integral of v du. Now I'm going to discuss the table method. So we're going to choose our u as the factor which gets simplified or which gets reduced upon differentiation, and we're gonna choose dv as the other factor, so u and dv. So first we choose u and dv. So I made two columns. One column is called d, other column is called I. So d here stands for differentiation, so here we're gonna do repeated differentiation of u, and here we're gonna do repeated integration of dv. So in the first column of the table, or the D column, we're going to write all the derivatives of u. So first derivative is u prime, second derivative of u, third derivative of u, fourth derivative of u, and keep on going, nth derivative of u. So I will tell you later on when to stop. It depends on problem to problem. So I'll discuss the different cases, like which tells you where to stop while doing the differentiation. Similarly, in the second column, I column, we're going to take the integrals of dv. So first integral, let's say v1, and then in second integral v2, third integral v3, v4, and so on. You can keep going. So once we found all the derivatives and integrals, so in case of repeated integration by parts, what we do, so we multiply diagonally. So we multiply our u with v, first derivative with the second integral, and so on. And the last one we multiply horizontally, and we take the integral of last row. So integral of last row's multiplication. So we take that. And as far as the signs are concerned between these terms, so first we start with the positive sign, and the next diagonal product will get a negative sign. And again, the next one will get a positive sign, and the next one will get a negative sign. So we alternate the signs, positive, negative, positive, negative. So in order to add or subtract the terms, and this is how we're going to write our final answer. So it will be more clear with the example. So let's start with our first example. So we need to find the integral of x raised to power 5 sine x over 2 dx. So we have an algebraic function and we have a trigonometric function here. So first step is you choose your u and v. So u and v, so the one which becomes simpler on differentiation will be our u. So in this case it seems x raised to power 5 is going to be our u, or if you want you can use your rule of thumb that we discussed in the last video. So isolate. So since in this one algebraic comes first, so whatever comes first should be your u, and trigonometric comes after, so whatever comes after should be your dv. So we set up our two columns in the table. So one column is the differentiation column, so D column and I column. So in D column, we put our u is equal to x raised to power 5, and v is equal to sine x over 2. So derivative of x raised to power 5 is 5x4. Derivative of x raised to power 5x raised to power 4 will be 20 x cubed, and if you take next derivative that will be 60 x squared, and next one would be 120x, and then we get 120, and then we get 0. So it means we get 0 as the derivative. So this is where we need to stop. So thus our first stop is when the derivative becomes 0. So that's our first rule of stopping, when the derivative becomes 0. Similarly, in the other column, we're going to integrate our dv again and again. So in this case, sine x over 2. So if you integrate this, the first integral would be, so integral of sine is negative cosine x over 2, and also we need to divide by 1 over 2. So in this case, we get negative 2 cosine x over 2. Similarly, for the next one, integral of cosine is sine. So we get, and another 2, so we get negative 4 sine x over 2. And again, integral of sine is negative cosine, and taking care of the negative and another 2, we get 8 cosine x over 2, 16 sine x over 2, negative 32 cosine x over 2, and in the end we get negative 64 sine x over 2. Now, in order to write the solutions, we're going to multiply the factors that are in the diagonal. So we're going to multiply this factor with this with this with this with this with this, and in the end, we're gonna do our horizontal multiplication, and we're gonna take integral of this horizontal term. And signs that we're going to use in these diagonal terms. So we're going to use positive alternatively, positive. So this is positive, so that, and one would be positive. And we're going to use negative for this, negative for this, negative for this. So alternatively, we're going to use positive and negative signs in between the terms. So let's write our solution now. So our first diagonal tells us we should multiply x raised to the power 5 and negative 2 cosine x over 2, and this term should be positive. So next, minus, so 5x raised to the power 4 times negative 4 sine x over 2, and then again plus 20x cubed times 8 cosine x over 2, and then we have minus 60x squared times 60x squared times 16 sine x over 2, and then we have plus 120 times negative 60, oh sorry, 120 times x, and negative 32 cosine x over 2, and then we have minus 120 times negative 64 sine x over 2, and for the last term we have positive sign, and we should take integral of the last row, so integral of the product in the row, so 0 times something, so that will be just integral of 0 dx, so which of course is just 0, and then plus c. So overall, we got this as our solution. So I'm just gonna write it nicely. So negative 2x5 cosine x over 2, then negative, negative, positive, positive 20x raised to the power 4 sine x over 2, and then plus 160 x cubed cosine x over 2, and then we have 16 times, okay, so negative 960 x squared sine x over 2, and we have negative, so if you multiply these two together, 3840 x cosine x over 2, and plus 7680 sine x over 2 plus c. So this is what we get after the integration. So we use the table method here, but if we use our original method of integration by parts, so we have to repeat the process so many times. But the table method definitely it saves us time, and it helps us to solve the multi step integrals in no time. So from this example, we learned that so we need to stop in the table when the derivative becomes 0. Let's take a look at this example. So in this one, we have integral of e raised to power 3x sine 4x dx. And using our mnemonic isolate, we know that whatever comes first should be our u. So here trig function should be your u and other one should be your dv. So we're going to set up our u in our d column and our dv in our I column. So in this case, u is sine 4x and dv is e raised to power 3x dx. So e raised to power 3x is our integral. It will be in our integral column. And now we're going to take the differentiation. So derivative of sine is cosine, and by chain rule we need a 4 here. So similarly in the next step, derivative of cosine is negative sine, and by chain rule another 4, so negative 16 sine 4x, and you can keep on going. So derivative of sine is cosine, so negative 64 cosine 4x, and you can keep on going. So it's never gonna be 0. Similarly, in the other column, we're going to take our integrals. So integral of e raised to power 3x is e raised to power 3x divided by 3, so 1/3. And then in the next step again, 1 over 9 e raised to power 3x, 1 over 27 e raised to power 3x, and you can keep going. So now the question arises that in this case, our derivative and integral keep on going and we never get to a stopping point. So when should we stop? So we should stop at the point when you get the same factors as the original integral in a row. So in this case, you have e raised to power 3x and sine 4x in your original integral. So when you get these two factors in the same rows, you should stop. So we notice that sine 4x, okay, we have sine 4x in the second here, and also e raised to power 3x. So we should stop at this point. So second stop method is when the factors in a row repeat. When the factors in a row repeat, so we should stop. Or in other words, when you get the same factors as in the original integral in same row, you should stop. So let's use our table to write the solution to this integral. So first we're going to go diagonally, and for this one we're going to use a positive sign. We get 1/3 of e raised to power 3x times sine 4x. Then we're going to take the next term. Again, we're going to go diagonally and we're going to use the negative. So negative of 1 over 9 e raised to power 3x, and then 4. So I'm just going to write 4 here. So cosine 4x. And lastly, we should go horizontally and we should take the integral of last horizontal row, product of the factors in horizontal row. So in this case, we get the sign is going to be positive. So we have positive here and we have a negative here. So overall, it's going to be negative. So negative of, so 1 over 9 and 16. So 16 over 9 integral of e raised to power 3x sine 4x dx. Now we notice that we have the same original integral here, same as original integral. So it means we can bring these two together and we can simplify it further. So adding 16 over 9, it is integral of 3 raised to 4x sine 4x dx on both sides, we get, so 1 plus 16 over 9 integral of e raised to power 3x sine 4x dx, so equals to, so what we already have is 1 over 3 e raised to power 3x sine 4x minus 4 over 9 e raised to power 3x cosine 4x. And in the next step, So this one is 25 over 9. So since our goal is to find this integral, so in the next step, we're gonna divide both sides by 25 over 9, and we get integral of e raised to power 3x sine 4x dx. And here we get 9 over 25 times 1 over 3 e raised to power 3x sine 4x. And again, dividing this side by 25 over 9, we get 9 over 25 times 4 over 9 e raised to power 3x cosine of 4x. And of course, it is an indefinite integral. We need to add a c. So in the last we got, so bit of simplification. So 3 over 25 e raised to power 3x sine 4x minus 9 and 9 cancels. 4 over 25 e raised to power 3x cosine over 4 cosine 4x plus c. So that is our required solution. And if you want, this is optional, you can take the common factors out. So e raised to power 3x is a common factor and 1 over 25 is a common factor. So you can take them out. So we get e raised to power 3x over 25. So inside you're left with 3 sine 4x minus 4 cosine 4x plus c. So that is our required solution to the integral that we were solving for. So from this example, we learned that sometimes in the table method, if differentiation never ends, so we stop when the factors in a row repeat, or when the same factors that we had in the original integral, they occur in the same row. Let's take a look at one more example. So in this one, we have integral of x raised to power 5 ln x dx. So using our islet, so we have to choose our u and dv. So our u should be our logarithmic term, so u should be ln x, and our dv should be algebraic, so dv should be x raised to power 5 dx. So we set up our table. So in the d, we're gonna write our u, and in the I column, we're gonna write our dv. And then we're gonna start showing the derivatives of ln x. So the derivative of ln x is 1 over x. Derivative of 1 over x, so which is x raised to power negative 1. So using the power rule, we get negative x raised to power negative 2, so which is negative 1 over x square. And similarly, if we take another derivative, we get 2 over x raised to power 3, and so on. So we can keep going. Similarly, when we take the integral in the second column, so we get x raised to power 6 over 6. And then in the next step, we got 1 over 6 x raised to power 7 over 7, which is 1 over 42 x raised to power 7. And in the next step, again, we can get 1 over 42 times 7, 42 times 8, sorry, and x raised to power 8. So 42 times 8 is just 336. And we can keep on going. There is no stopping, because we see that the powers keep on increasing even though they are in the denominator, and here again the exponents keep on increasing. So how do we decide where to stop in this case? So we stop, in these cases, we stop when we can integrate the product of a row. So whatever the first product of a row is easier to integrate, we stop. So stop when you can integrate a row. So in this case, we notice that if we take the product of ln x and x raised to power 5, we don't know how to do this integral. But if we look at this row, 1 over x times x raised to power 6 over 6. So this is integral of x raised to power 5, which we know how to do using the power rule. So it means that is the good time to stop. So we just stop at our second step here. So we stop here. So when you can integrate the product of the row, you stop. So it means we don't need this. Thus, we're gonna first write our solution. So we're gonna do the product of diagonal, and we're gonna add positive sign. And since then we are stopping at beyond above this red line, so Now we have only option. Second term is gonna be the integral of this horizontal row, and for that we need to use our negative sign. Thus the solution becomes, so x raised to power 6 over 6 times ln x, positive term, minus integral of product of 1 over x raised to power 6 over 6 dx. So in the next step we get 1 over 6 x6 ln x minus, so 1 over 6 outside, integral of x raised to power 5 dx, and 1 over 6 x raised to power 6 ln x minus 1 over 6, and integral of x raised to power 5 is x raised to power 6 over 6 plus c. So overall we got 1 over 6 x6 ln x minus 1 over 36 x6 plus c. So this is our required solution in this case. Thus from this example we learned that while using the table method, so we need to stop when you can integrate the product of a row. So to summarize again, for tabular method or for DI method, for integration of parts, integration by parts, we set up two columns. One is for the u term, other is for the dv term, and we do the differentiation of the first column, integrals of the second column, and then we add or subtract the terms diagonally, and we take the integral of the product of last row. And in summary, we stop when making the table, we stop when the derivative becomes 0, or for the never-ending derivatives, in the case when the derivatives are never-ending, we stop when the factors in a row repeat. In other words, when we get the same factors as in the original integral, or we stop when we can integrate the product of a row. I hope you enjoyed this video, and integration by parts makes sense to you now. In the next video, I'll discuss when we have integration by parts and definite integrals together and what to do in that case. Thanks for watching. If you like this video, please hit the like button or subscribe to my channel. See you again.